All right, so looking at the cardiac cycle, this is slides 20 through 33 in chapter 15. We're going to put together a lot of the things that we've already looked at with the heart. So remember that there's four chambers. We've got a right atrium and a left atrium, a right ventricle and a left ventricle. On the right side, the right atrium and right ventricle deal with deoxygenated blood. The left atrium, the left ventricle deal with oxygenated blood. So we're going to look at how we move through the heart and the different words that are going to be associated with some of these things. So right off the bat, we're looking at some words that I hope everybody's fairly familiar with. Systole and diastole. Systole or diastole. There's different ways to pronounce it, but they're the same word. Now, systole means contraction, to contract. Diastole or diastole means to relax. And so if you know which chamber is, that tells you what chambers are up front. If you know what chamber it's talking about, it tells you what's going on. Atrial systole is atrial contraction. Now, the atrium's not going to contract all that much. It's more like a gentle squeeze, so to speak, unlike the ventricle, which its systole is very strong and powerful. So the way that the heart functions is, like I said, as a pump, and there's basically two pumps, the right side and the left side. The right side's a pump that's going to go to the lungs. The left side's a pump that's going to go to the body. So in order to move the fluid, the blood, through the heart in an orderly manner, we have to have regulation of how it pumps. It can't just squeeze all at once. It has to have a flow to it. So atrial contraction, called atrial systole, during that time the ventricle will relax, called ventricle diastole. When ventricles contract, ventricles systole, the atrials relax. And so it's kind of this wave that goes through. Now, if you're taking blood pressure, like normal blood pressure is 120 over 80, and we'll talk about blood pressure in another video, understand that it's always measured in millimeters of mercury, mmHg, whatever the case may be. Right now I just want you to, most people know this number, and most people would know that it is systole over diastole. And you should know that simply because if something is under pressure, if it's contracting, it's putting something under pressure. So if it's under pressure, it's going to have a higher number. Systolic numbers are the high. Diastolic numbers are the low, because it represents when the pressure is low. All right, so we're going to kind of move through this. Now, you're going to see that there's a time when we're going to talk about these that instead of systole, we're going to use contraction, and instead of diastole, we're going to use relaxation. And there's also a time when we're going to look at these through the cardiac cycle as far as the electrical impulses that go through. And systole, which is contraction, also means depolarized, because depolarized is when something's going to send a signal in the nervous system. And so this is looking at the signal. It's the signal that passes along that causes contraction. And diastole is repolarization. All right, so all these kind of tie in together. So let's move along. Should have taken this out. Remember that all of these little red banner ones, not really going to test you on. They've got good information, some interesting things, not going to test you on it. So the cardiac cycle, this is where we get back into what we're talking about. The cardiac cycle, the pressure of the heart chambers rises and falls, and it changes the valves to be open or closed. So let's say, I'm going to look at it just this way, and I am going to, well, that was getting slack with my wording. I'm going to draw this as a door that moves in and out. And then in the entry door, this one is going to move in and out. All right. So, and actually I'm going to erase those. So what's going to happen is when I put pressure and squeeze this, the pressure is going to increase, and this door right here is going to slam shut and close and prevent anything from trying to get out. Woo, that was a bad little error there. Anything from getting out this way. So it takes this and blocks passages off that, and the blood gets squirted out through that door. All right. That is systole. That is ventricle contraction. Now, if I was going to say ventricle relaxation, so now these go out this way and this causes a decrease in pressure, but the way the average person would say it would be a suction. And so as this suction happens, I'm going to have this door slam shut, and the things that want to come back in can't get in. And then this one is going to be open, and so the blood that's in the atrium is going to get pulled into the ventricle. That is how it works. Pressure causes, or contraction causes pressure. That's going to slam the door that's for the blood trying to get out to prevent it from going in the atrium. The blood gets pushed out into the vessel, either the pulmonary trunk or the aorta. When the ventricle relaxes diastole, it's going to cause a suction. It's going to cause those semilunar valves to close, and then it's going to open the AV valves, and blood that's in the atrium gets pulled into the ventricle. So this is what it's going to talk about. During atrial systole, contraction, and ventricle diastole, relaxation, the ventricles relax, the AV valves will open, the semilunar valves will close. Entryway opens, exit is blocked. About 70% of the blood flows passively into the ventricles. The atrial will go through systole, which is just a general squeeze, which the rest of the blood will go in. Now, right after that happens, the ventricles will start to squeeze, ventricle systole. Now, when this happens, the atrium will start to relax, which is called atrial diastole. The AV valves close. The entryway gets blocked off. Now, the exit is going to open, but the entryway gets blocked off because we've got these chordae tendineae that are attached to the papillary muscles that prevent the AV valves from going back into the atrium. So the blood is going to go from the ventricle, I'm trying to write this here without crossing over it, but I did, into the pulmonary trunk or the atrium. So the semilunar valves are going to open. So the exit gets opened. So I'm going through this process of having the doors swing. One opens, the other closes. One opens, the other closes. So this one closes when this one opens, and vice versa. And so the blood's going to come in, fill in the little spot in the ventricle, and then pushed out. It's going to come in, fill in the ventricle, get pushed out. Now, when we listen to heart sounds, which listening to any body sound is called auscultation, and that's a part of lab that you'll need to know. But any part of listening to a heart sound is about you're listening to the valves, because what you're hearing is the valves opening or closing, and it's kind of an echo that you're going to hear. And so you're going to hear two different sounds, and they are described as lub and dub. Now, this is called lub and dub. I've always heard it with these as B's, but it doesn't matter. L and B, lub, dub. Now, most people have probably heard of this, lub, dub, lub, dub. Lub is the first heart sound. Dub is the second heart sound. They are referred to, the sounds are referred to as S1 and S2. Now, hopefully you can figure out S1 means the first heart sound. So lub and S1 are the same. Dub and S2 are the same. Again, it shouldn't take too much mental energy. I'm making too many of these, I think. Too much mental energy to have S1 and realize it's the first heart sound and S2 is the second one. So lub is S1, dub or dup is S2. Now the first heart sound is this. When we are going to start the cardiac cycle, it starts with the ventricles at their most relaxed point, and the first action is going to be that the ventricles squeeze. They go through systole. When systole happens, again, so I'm going to draw this little flow chart here, and when systole happens, I'm going to have the walls of the ventricle contract. That's going to increase the pressure inside the ventricle. Blood wants to escape. So the semilunar valves, which are over here, and I'm just drawing them as a little thing, open, blood escapes. The AV valves get slammed shut. So the sound you hear is the sound of the AV valves closing. And so S1, which is called lub because it sounds like lub, is the sound of the AV valves closing. S2, dub, is when the ventricle starts to go through relaxation. When the ventricle relaxes, right, we're going to have a suction in here, so blood's going to be pulled in. Since the semilunar valves are the exit, they slam shut to prevent blood from coming in, and blood comes in through the atrium. So the sound you hear in dub or S2 is the sound of the semilunar valves closing. And this is important to know, and it will be a question in both the lecture and the lab. Lub is S1, and it is the AV valves, and it is ventricle systole. Dub is S2, which is the sound of the semilunar valves closing, and it is the sound of ventricle diastole. Again, very important to know that pattern. Now, a murmur is when the blood, let's say we go back to the idea of contraction, because this is when the pressure is really, really big time in this area. There are times when the AV valves don't close all the way, and instead of all of the blood being pushed out into the aorta, the pulmonary trunk, some of it, so let's say it closes almost, but some of the blood will be pushed back into the atrium, and it'll cause this little sound like a kss, and we call it a murmur, a swish. So they're called a murmur, and all that is not an incomplete closure of the cusp. And so the one that's under the most pressure is on the left side, called the bicuspid or mitral valve. And so mitral valve prolapse is when the mitral valve is being pushed back into the atrium. All right, moving on. So these are the areas. There are 4 areas where you will see or listen to, and I'm just drawing them because there's 2 sets. There's 4 valves. Now, when you are studying the skeletal system, hopefully it was pointed out to you that there is a very important landmark right here where the manubrium and the body of the sternum meet, called the sternal angle. Now, this is rib 2 comes into here. Rib 3 is here, so this little space in between 2 and 3 is called an intercostal space. Well, that intercostal space on either side of the sternum is where you will hear the semilunar valves. Now, you're going to hear both lub and dub. You're going to hear both, so S1 and S2, AV and semilunar. Right? So we're on all this. All right. So you're going to hear both of them. But the one that is the sound for the semilunar valves is going to be the more prominent one here. It's going to be the sound that's the loudest. So here you will hear S2 the loudest. you will hear dub the loudest. And so you can isolate it and say if it's on the right side of the sternum, it's the aortic semilunar valve. If it's the left side of the sternum, it is the pulmonary semilunar valve. Now, if we go down, you can feel where the point of the sternum, the xiphoid process is. Basically, you feel where the ribs, the bottom ribs join. You feel for the first intercostal space that's kind of prevalent on the left side, and this is the tricuspid area, the right side, the right AV valve. Now, you're going to hear both lub and dub here, but this one you're going to hear lub or S1 more pronounced. Same as this. So when you hear this one, the tricuspid valve, if you slide over and drop into the next intercostal space, this is where you'll hear the mitral or bicuspid valve. Now, these are really important things to know in nursing. When you get into nursing and have to name these and have to say where they are, this is a really important thing to know. I'll probably be one question on the lecture test on here, but as far as areas, this right here, up here, this is where most of the questions will be, knowing things about these. So now, skeletal muscles work together to work as one entire group. All right, so the intercalated discs that you looked at, the darkened lines that you saw in skeletal or in cardiac muscle, or where the cardiac muscle actually bind together. This is where you're going to have desmosomes and gap junctions. Now, the desmosomes are for strength. The gap junctions are so the fluid can pass from one cell to the next so that the electrical impulse and everything function as one unit. That's why it is called the functional syncytium. I hate that word. I don't even know that I'm pronouncing it right. I do believe I am, but if I'm not, forgive me. But the word means in sync. If you've ever heard of in sync, and I'm not talking about the boy band, I'm talking about what the phrase in sync means. It means all together. That's what this is. It's functionally in sync, all right, because of these gap junctions and the way things are bound together. So there's two main areas. And again, we'll go back to the atrium and the ventricle. So the atrial syncytium is the first. The atrium both squeeze, push blood into the ventricles. Then the ventricles squeeze and they push blood out of the heart. So when the ventricle walls contract, it's called ventricular syncytium. Now there is a pathway of this contraction, and in the skeletal muscle system, you learn that the muscle membrane, the cell membrane, had a unique name, right? The sarcolemma, and it's because the cell membrane of a muscle, any muscle, really is like a axon in a nerve. It is designed to transmit a signal. So we have a conducting system in the muscles of the heart, in the cardiac muscles, and it's what coordinates these events. And it starts with a thing called the SA node, and we will look at this in the next slide, I believe. It is what is referred to as the pacemaker of the heart. Your heart can beat if you cut off all neural connection to it. As long as it has blood flowing to it and oxygen getting to it, this SA node will continually cause the heart to beat. Now, it passes along between the right and left atrium, and this is the part we just looked at where we called the atrial syncytium, and it will all converge together on the AV node. So you've got the SA going to the AV. So the A's kind of connect each other. The AV node is pretty much right in the middle between the two atrium and the two ventricles. It's really on the atrial side, but it's between all those. So if I was to draw the heart and kind of divide it up, which again, this isn't what the heart looks like, it's really going to be close to this little area here. It's going to pass along on this bundle. It's a bundle of muscles / nerves that are going to go through, and they divide into bundle branches. So if I'm right here, and this is, we'll say this is between the two ventricles, and so I've got this interventricular septum here, this muscle, I'm going to end up having a bundle that goes down each side, which we call bundle branches, that are going to work for each side. So this is working on the left, this is working on the right. Now this is all one band of muscle. Now, once it hits the bottom, it is going to bounce up along the outer walls of the ventricle on things called Purkinje fibers. And so when this hits, it is going to cause all of the muscle to contract, and then it's going to cause the muscle to contract and squeeze the ventricles. I'm going to try to put up a video. It's not on here, but I'll try to put up a video that shows this, or give you a link to it, to kind of show how this works. Because when you see it, it makes perfect sense. When I'm going over it, I know it can be very confusing. So this again is another way to look at how it goes through, another way to write it out. But this is the picture that really does the best job. So I have an SA node, remember the pacemaker of the heart. It's going to send a signal. We call this the atrial syncytium. All of these are going to cause the atrium to contract, and then all of these impulses are going to gang up on this thing called the AV node. There's a spot here called the AV bundle, and this actually is going to cause the impulse to kind of slow down. So it's real quick in here, and then it's going to hit this thing called the AV bundle, and it'll slow down. So it's quick, and then a little part slow, and then quick again. Well, that was kind of interesting. So once it hits that, it's going to branch. It's going to get into this interventricular septum, and it's going to branch, and I'm going to have a right and left bundle branch. It goes down to the apex of the heart and then bounces back up, basically. These are called Purkinje fibers. And the Purkinje fibers are not only along the wall, but they are going up into these papillary muscles to cause everything to contract very quickly. So I hope that kind of helps when you kind of see it. Now we can measure the electrical impulse as it goes through the heart, and it's called, most people know it as an EKG. It should be called an ECG, Electrocardiogram. This is the German, and it's a K. So it's a recording of the electrical changes as it goes through. And this is where we'll start looking at these terms, depolarization and repolarization. Depolarization is contraction, systole. Repolarization is relaxation, diastole. And so you gotta be able to juggle those terms in your head to understand which is which. So the P wave, we have this little wave up front called a P wave, and it is where the atrial starts to contract. Boom, it says it's just prior to it. So the atrium contracts, and then we have this huge thing called the QRS complex. It's 3 waves all together. Ventricle depolarization, which is going to, this is where that big spike and then the drop is. In this QRS complex, the atrium is going to repolarize or relax, but it's overshadowed by the QRS. And then finally, the T wave at the end is ventricular repolarization. It's starting to relax again. Again, this part here kind of tells you what I just mentioned, that the QRS complex swallows up atrial repolarization. So this is a picture of it. I should have really kind of enlarged this a little bit. But if you've ever seen a soap opera, this has been on the background. Most movies will have something on here. It is one of those things that's pretty popular. Most people don't even know what they're looking at. So this is kind of showing the process, the steps that go through, down through here. And so we have the P, the QRS, and the T. Now we're only looking at normal in here. We're not going to get into what abnormal is, but that is what you would be looking at. Any lag time between them, any invert waves, stuff like that, you can kind of see something's going on. But this is a normal. This is a very weird chart, and I like looking at it, but it is an odd chart. This has nothing to do with what we're looking at. This is going to be pressure, the amount of pressure as we go through ventricle diastole, ventricle systole, ventricle diastole, ventricle systole. And so it's looking at the change in pressure. This is looking at the change in volume. Obviously, as we go through ventricle contraction, we're going to have a decrease in volume. This is the ECG here. This is the one that we were just looking at, and the only one I'm really worried about. And then this is talking about the heart sounds, just looking at the actual audio track of what it would look like, the little vibrations. So anyway, I always think this is a really weird thing. This is the only one that I would go over and that you're holding responsible for, and it is simply understanding what the P, QRS wave and the T waves represent. Now, the cardiac cycle is going to be controlled by the SA node mainly, but we also have sympathetic and parasympathetic fibers that will help modify the heart rate or change it a little bit if needed. Now, understand sympathetic, fight or flight. What do you think it's going to do to your heart rate? If you're scared, does your heart rate go down or does it go up? Right? The sympathetic nervous system is going to raise heart rate. Parasympathetic helps calm it down. Now, most of these are going to be associated with the sympathetic nervous system. Fight or flight. Body temperature gets too high. That's the sympathetic nervous system kicking in. Physical exercise. That's the sympathetic nervous system kicking in. We can have some issues with some ion issues if we have too much calcium, too much potassium, not enough calcium, can change things. So the one thing I really want you to take away here for the parasympathetic is it slows down the heart, but it does it through the vagus nerve. Remember, cranial nerve 10, the vagus nerve, is a very important nerve to remember. It is the parasympathetic nervous system from your chin down. If you go back into, I believe it's chapter 11, when you go over the cranial nerves, look at that chart that shows all the things that the vagus nerve controls, and you will see that every organ has a vagus nerve innervation to it because it is the parasympathetic nervous system. So sympathetic nervous system is going to have, they call it accelerator nerves. What do you think that's going to do? It increases heart rate. And so our body is going to be monitoring that. We're going to have what are called baroreceptors, which are measuring pressure, which we'll look at in the next video. And it's going to help control what's going on. If my blood pressure gets too low, I got to speed up heart rate. If it gets too high, I try and slow it down. Most of these reflexes are going to be controlled in what is called the cardiac control center of the medulla oblongata. And remember, anytime you're in a bad mood, say this word. It is fun to say, and it's hard to say it without at least cracking a little bit of a smile. All right. So this is the medulla oblongata is going to play the balancing act between the parasympathetic and the sympathetic nervous system. So again, the cardiac control center regulates the autonomic impulses to the heart. And since we're talking about the autonomic, the automatic pilot, we're talking about parasympathetic and sympathetic. And parasympathetic is going to be the vagus nerve, right? The vagus nerve is going to be the part that's going to be used to control the parasympathetic. Now, what two neurotransmitters would these have? Sympathetic and parasympathetic. So if I go back here, the parasympathetic uses acetylcholine. I'm just going to put ACE. Sympathetic uses epinephrine, our buddy epinephrine. And again, remember, epinephrine means above the kidneys. Adrenaline, ad means above, renal means kidneys. Epinephrine and adrenaline are the same substance, but there was someone who patented or trademarked the term adrenaline, so we can no longer call that substance adrenaline without paying him a fee. So we use the word epinephrine. Now, most of us know what adrenaline does. You instinctively know, gives you energy, is about fight or flight, really. So remember, epinephrine, adrenaline, same thing. So when we're looking at how this is all controlled, there are two areas of control that our body's using to monitor, and they are little receptors that are in the carotid arch, the carotid sinus, I should say. The carotid baroreceptors are here, and then the aortic arch, we have aortic baroreceptors. Now, I want you to think about this. If I want to measure the pressure in the entire system, I want to go right to the source. Everything that's oxygenated that is going out to your body is going to go through the aorta right here, especially the ascending aorta. Before it goes anywhere else, that's where it's going to go. So if I want to measure the pressure and get the best idea, that's where I'm measuring it. Now, above this, there is this really important gray wrinkly thing called the brain, right? And the brain, I want to do everything to protect. So I want to measure the blood pressure right before it gets into that cranial cavity. And what do we know? The carotid sinus is where that happens. So it's where these little measurements are taken is well controlled. It is definitely at the best possible place. The beginning to measure everything, and then right before it enters the cranial cavity to measure the brain, to keep our brain safe.